Okay, we're going to talk about 3.11 hyperbolic functions. We're going to go over this section quickly. The goal here is just to give you a quick introduction to the hyperbolic functions and talk about their derivatives. Some of you are going to see this as a part of your degree program, some of you aren't. So just a quick introduction so that if you see these you're not freaking out. So anyway, take a look at these down here actually. SINHX, it looks like sine, but it has an H in it. And you'll see actually all the trig functions that you know with an H inserted here before the of x part is actually a hyperbolic function. And so the hyperbolic functions are actually not trigonometric functions. So let's look at sinh of x, or hyperbolic sine of x, is actually e to the x minus e to the negative x over 2. So notice that there's no trig stuff in here. There's no sine function, any other trig function in here. So it seems super weird that you have like this trig-like notation when this function depends on e to the x stuff. So there's an explanation for that. First of all, look at cosh, or hyperbolic cosine, and notice it's very similar to sinh, except it's plus. So these are closely related functions, but they're not exactly the same. And by the way, I forgot to mention in the beginning of this section that you do not have to memorize anything from this section. You don't have to memorize the definition of sinh or cosh, the derivatives, anything. Graphs are not going to really even use anything. I'm just kind of showing them to you so you know what they look like. But basically I'm going to give you everything you need. You just need to know how to use it to answer the problems. Anyway, so here's where the trig-like notation comes in. It is there for a reason. Sinh and cosh are the primary functions here in this family of hyperbolic functions, and then we define the rest of the hyperbolic functions in terms of sinh and cosh. So a lot of these are pretty much, or I should say all of them, are what you would expect. Cosecant, or hyperbolic cosecant, is what this one is, the third one in the top row, is 1 over sinh. Okay, so that's just exactly what it would be if it was cosecant of x. Would be 1 over sine of x. So anyway, notice that these are all defined like the trig functions. So where the trig function thing comes in, these names make sense. Overall, the sinh and cosh and the hyperbolic thing is that these functions have a relationship with a hyperbola that gives them properties that are kind of work out a lot like the trigonometric identities. So some of them are actually the same relationship as with the trig function's relationship to the circle, and some of them are just off a little bit by a sign or something like that. So a little confusing, but when you see this notation with the h in it, it is not a trig function. It has kind of that notation because there are some properties that are similar to trig properties, but it's actually functions that on the baseline for sinh and cosh, which everything else is defined in terms of, are e to the x stuff. And again, you're given those definitions. So, I mean, if you forget, just look at it. It should come back to you. So what do the graphs of these things look like? So in blue is a graph of sinh, and notice that the definition of sinh, e to the x minus e to the negative x over 2, can be broken into two terms. And then you're just looking at a combination of e to the x divided by 2 and e to the negative x divided by 2, which are shown here in purple and olive green. And so if you subtract those, then what you'll have is the blue line. So this graph kind of looks like a parabola, something like y equals x cubed, but the slope is such that it's, not quite the same. the graph of y equals x cubed would be much more pronounced, and the slope change is different, but kind of looks that way. Cosh is the blue line in this next graph, and notice it kind of looks like a parabola, kind of like y equals x squared kind of thing going up, translated up one. But again, the slope of this is a little different, and what it is e to the x over 2 plus e to the negative x over 2, so again showing those two terms, their graphs, and if you sum them you get the blue line to kind of show you where that comes from, or why that graph would be what it is. But it turns out this change in slope here is such that it's just not y equals x squared. Now tanh looks like this. I won't even really talk about that, but just in case you're curious what tanh looks like, there it is. Alright, so why are we studying these? A famous example, and you'll see this on the homework too, is something called a catenary, and that's basically the graph y equals cosh, or hyperbolic cosine, with some translation scaling functions here applied to it. And so a catenary is the shape that's made when you have something like a line or a rope that has some non-negligible weight, and it's allowed to hang due to gravity between 2 points. Then the shape that's formed, because it is hanging under its own weight, is actually can be represented with cosh. So that's why we care about it. And so engineers are going to definitely see this. So what I said before about the properties being kind of similar, for example, cosh squared minus sinh squared is 1. It's kind of like cosine plus sine is 1, the Pythagorean theorem, not Pythagorean theorem, Pythagorean identity. But, you know, it's a little different because it's minus. So you don't have to know that. It's just kind of illustrating that. Derivatives of hyperbolic functions. So these are all given, but notice these two have similarities with the derivatives of the trig functions. So here we go. The derivative of sinh is cosh. Derivative of sine is cosine. So that's like follows what you would expect if you thought, hey, it's going to be kind of like the trig functions. There are some exceptions. The derivative of cosh is sinh. Derivative of cosine is negative sine, so that's a little different. And so I just give these to you. You don't need to memorize them. Just want to point out that some of these are exactly what you'd expect from the trig functions. Some are a little different. So in other words, look at the information that's given or the note sheet. And I'll have a note sheet on Moodle that shows you everything from 3.11 that I would give you. Normally what I do on a quiz or a test is I just give you like a selection of that sheet, just because to save paper basically and kind of narrow it down so you're not having to search the whole entire sheet in that test scenario. One thing you'll have to do is show a derivative rule, kind of like we did with the trig functions. Strategy is going to be a little bit different here. For this one we have the derivative of sinh is cosh, so that's the derivative rule for sinh. What you'll want to do is just write the definition of sinh, and then you actually know how to find that derivative. So one way to do that derivative is to take a 1/2 out, and then note you can just avoid using the quotient rule and take the derivative of each term separately and use the constant multiple rule. E to the negative x involves the chain rule. Other than that, it's pretty straightforward. And then that just gets us to the definition of cosh, which is also given. So again, you don't need to memorize these, you just kind of have to remember. It's helpful to remember, like, oh yeah, to show this identity, not identity, to show this derivative rule, I just use the definition. So I got a little lazy here, but there are 6 inverse hyperbolic functions which potentially would be given. I just wrote down kind of the top 3. You can see they're kind of complicated, And you can also take derivatives of hyperbolic inverse hyperbolic functions. So I got lazy here, even just writing it down. Inverse hyperbolic functions. So I would give those to you, expect you to apply them. Notice the similarities with the inverse trig functions, which is sort of why they have these names. But again, similar properties, similar derivatives to the trig functions, but they are not trigonometric functions. Little subtle difference there, but important. So now we're going to run through a bunch of examples. So black. So, first of all, we're just going to find some derivatives. First one, we have y is equal to the natural log of sinh. Kind of the short name for hyperbolic sine. So notice here, it's the natural log of sinh. So finding the derivative involves the chain rule because it's a composite function. Derivative of natural log of x is 1 over x, so the derivative of the outer function evaluated the inner function is 1 over our inner function, or 1 over sinh. And then with the chain rule, you have to multiply by the derivative of sinh, or the inner function, which is cosh. And notice we can write this really nicely. Cosh over sinh is hyperbolic cotangent, which I avoided saying its nickname because it kind of sounds gross. Koch. Alright, next thing. Let's find the derivative of y is equal to x squared times tanh of 1 over x squared. Alright, what's the big picture here? Big picture is we have x squared times tanh of 1 over x squared. So notice the big picture is we got a product going on here. So I'll write this a little bit more obviously as a product. Also, I'm going to prep the 1 over x squared as x to the negative 2. Get it ready. So taking the derivative, I have my f, which is x squared, and then the derivative of tanh of x to the negative 2 involves the chain rule. I'm just going to go ahead and do it. The outside function is tanh. Its derivative, if you guessed it, is sech of the inner function squared. So I'm just going to get that squared ready. Inner function is x to the negative 2. That's the derivative of the outer function evaluated at the inner function. Then you got to follow up with the derivative of the inner function. In this case, x to the negative 2, its derivative is negative 2x to the negative 3. Okay, moving on. In the product rule, we have our f g prime. Now, our g is tanh. Oops. Of x to the negative 2. Just got to write that down. Derivative of x squared is 2x. This thing is really nasty. I'm not going to simplify. It doesn't really simplify that much. So that's good enough. Another one. Y is equal to inverse Koch of root x squared plus 1. Wow. You would be given this rule. And you'd be given these other ones, but I'm just going to write down the rule here because it's kind of a weird one that we wouldn't even probably guess. So the rule for hyperbolic, inverse hyperbolic cotangent, or inverse Koch, harder to say it than the result is 1 over, oops, see, I even forgot the derivative because there's just so much going on here, is 1 minus x squared. Okay, so now that is the outer function here. Using the chain rule, what we're going to have is 1 over 1 minus parentheses something squared, where that x is our, or something is our inner function, root x squared plus 1. So that's the derivative of the outer function evaluated the inner function. Then we need to take the derivative of the inner function, which itself involves the chain rule too. So 1/2 x squared plus 1, new power negative 1/2, multiplied by the derivative of x squared plus 1, which is 2x, and you're done. So this one actually does simplify a fair amount. Remember on the exam for sure, you're not going to have to simplify, but just to kind of practice a bit. Notice that we have a lot of simplifying going on here. Root square boils down to x squared plus 1 in parentheses, that negative up front. Then, writing this as a single fraction, maybe just notice this right from the get-go that the 2's will cancel, x is up top, and then we got root x squared plus 1 down low. Next thing, notice here when we distribute the negative, we have 1 minus 1, so overall we have 1 over negative x squared. So much fun simplifying. Next thing is a pair of x's. So this thing just really boiled down to negative of 1 over x root x squared plus 1. Beautiful. We're almost done. One last example. This is actually number 11. A suggested problem.